Okay, so we are going to be going over the 1985 AP Physics C Electricity and Magnetism free response question number 1. So, a capacitor consisting of conducting coaxial cylinders, radii A and B, respectively, in length L, is connected to a source of EMF. When the capacitor is charged, the inner cylinder has a charge positive Q. Neglect end effects and assume that the region between the cylinders is filled with air. Express your answers in terms of the given quantities and fundamental constants. And so if we look at this diagram right here, it shows a circuit with an EMF source and then the cylinder. We can basically kind of neglect the circuit. This isn't a circuit problem. It's not going to really factor into the problem. This is what we want to focus on. And so if we look at part A, use Gauss's law to determine an expression for the electric field at a distance r from the axis of the cylinder, where A is less than r, which is less than B. So what we're going to do for this one is we're going to use Gauss's law as the question says. So we're going to start by stating that the flux is going to be equal to the closed integral of E dot dA, which is going to be equal to Q enclosed, so the enclosed charge, over, epsilon naught. And so, because this is a cylinder, we're just going to call E, the electric field is just going to be E. So we're going to use E to represent that. And because this is a cylinder, the surface area of a cylinder, if you recall your geometry, is 2 pi r times the length, which is L. And r is the radius of the cylinder. And that's going to be equal to, it said, a positive Q. The inner cylinder has a charge of positive Q, so that's going to be equal to just Q over epsilon naught. And so this is a rather simple question because now all we have to do, all these variables are given in the problem, so we don't need to find any variables, is just solve for E. So divide by 2 pi RL. And so what we get is that the electric field at a distance r is going to be Q over 2 pi r epsilon naught L, or whatever you want to order the variables in the denominator. So that is your answer to part A. And so for part B, it says determine the potential difference between the cylinders. So it's talking about from here to there. So what we can first say is that the potential, V, is going to be equal to the negative integral of E dot dr. And so what we're going to do next is it wants it from A to B. That's the distance between the cylinders, or the 2 points. One's at A and one's at B. So the potential from A to B is going to be equal to, and now like I said above, potential is equal to the negative integral of the electric field with respect to like the radius. But if I don't want to work with negatives, I can flip those limits. So normally what we would have is this, V dot dr. However, if I don't, want to work with negatives, what I can do is that I can just flip them, put A on the bottom, B on the top, and now that negative is going to become a positive, and it's still the electric field dotted with dr. And so when I evaluate this, I have to plug in the electric field, which we solved in part A. So VAB is going to be equal to the integral of, and that was Q over 2 pi r epsilon naught. Sorry, 2 pi r epsilon naught L dr. And so what I'm going to do then is take out the constants in that. So that's the variable in this is r. And so our constant is Q over 2 pi epsilon naught L. So the potential VAB is going to be equal to the integral Q over 2 pi epsilon naught L times the integral of 1 over r dr. And so if you know calculus, the integral of 1 over x dx is the natural log of x. And so what we're going to have is the potential VAB is going to be Q over 2 pi epsilon naught L of natural log of r from B to A. And so when we solve this, it's going to be equal to, again, Q over 2 pi epsilon naught L. This is going to be the natural log of B minus the natural log of A. If you know your log rules, what that also equals is the natural log of B over A, because natural log of one number minus natural log of the other is just going to be the natural log of that first number divided by the second number. And so that is going to end up being our final answer right there for part B. And so on to part C. Part C wants us to determine the capacitance C aught of the cylinder. So capacitance C, we'll call it C aught because that's what the problem wants, is going to be equal to Q over V. That's the simple equation for capacitance. And so all we're going to have to do is we know the potential from the previous problem, and we know the charge on that inner cylinder is positive Q. We can just plug our numbers in. So that's going to be C aught is equal to Q over, and from the previous problem, this is kind of a big number, so we're going to Q over 2 pi epsilon naught L times natural log of B over A. And so one thing that we can do is, this is a fraction, and these are really multiplied. And so we're just going to simplify that fraction, just simple algebra. These Q's will end up canceling each other, because that's basically Q over Q. And so what we're going to be left with is this is going to move to the numerator. So that's 2 pi epsilon naught L over the natural log of B over A. And that is your answer to part C. And so for the next part, there's a little bit of information it gives us. It says 1/3 of the length of the capacitor is then filled with a dielectric of dielectric constant K equals 2, as shown in the following diagram. And so when we look at this diagram, obviously it tells us 1/3 is filled with this dielectric. And the crucial part that we need to understand is that these, it basically splits the capacitors, or the single capacitor, the cylindrical one, into two. You have the one here, and then obviously the other one right here. And so one thing you have to realize about these capacitors is that they are going to have the same potential. So let's look at this circuit again. This is actually one of the useful things about the circuit it gives us. If we think about this and we sort of draw our third, or the third filled with the dielectric, so we have the two capacitors, as charge flows through that circuit, it can either go through the capacitor and reach the EMF source again, or it'll flow through and go to the second capacitor and then come back to the EMF source. So that means that the two capacitors are in parallel. They have the same potential, so they're going to be in parallel, right? Because capacitors capacitors that have the same potential are in parallel. And so let's just call this right here, this is C1. Let's call this C2. So C1 and C2 are in parallel. So what that means is that capacitors in parallel, they add up to the total capacitance. So C total is going to be equal to C1 plus C2. And it wants the total capacitance and the new one is C. So that C total is really just going to be called C. And so another key thing we need to know is that when we're calculating capacitance, when there's a dielectric present, we'll call it C new, the one with the dielectric present, is going to be equal to K C aught, which C aught's the original capacitance. And so with this portion here, C1, that's going to be equal to K C aught. And so let's just rewrite this. So C, which is really C total, but C is going to be equal to 2/3 C aught, because 2/3 of that original capacitor, this right here, 2/3 of that is left the same. It isn't changed at all. Only 1/3 of it is filled with that dielectric. So 2/3 C aught plus 1/3 is filled with that dielectric, so 1/3, but it also has that dielectric, and like I said, the new capacitance is K times the original capacitance. That's going to be 1/3 K C aught. And so K was 2, so really this is going to be equal to 2/3 C aught plus 1/3 times 2 times C aught. So really C is going to be equal to 2/3 C aught plus 2/3 C aught. And when we simplify that, the total capacitance C is going to be equal to 4/3 C aught. And that is your answer to part D of this problem. And that concludes the 1985 AP Physics C Electricity and Magnetism question number 1 response.